Hi, my name is Dennis, and I'm going to present our work on learnable spatio-temporal map embeddings for deep inertial localization. We would like to localize users indoors to assist in navigating unfamiliar buildings. A user's smartphone inertial measurement unit, or IMU, is an excellent sensor for this due to its ubiquity and low power consumption. But inertial odometry methods, like idle odometry on the left in orange, tend to drift compared to the blue ground truth over time. Our method on the right in orange uses map information to reduce this drift. Maps contain a lot of useful information to fix drift. If the user walks the path shown in gray from t to t+4, but inertial odometry estimates the red path, we can use the fact that the red path passes through the obstacle to know that our estimate has drifted. The key question becomes using this information effectively. We know that an odometry-only system, like this particle filter, will drift over time due to the lack of external measurements to correct odometry drift. Therefore, we need to add an external measurement to the particle filter. We form this measurement by combining odometry with map information. We combine them via a learned map prior network, which outputs the likelihood that the user is at any given location in the map. This likelihood is used to get rid of unlikely particles and replicate more likely ones during particle filter processing. The map network consists of two branches, one spatial and one temporal. The spatial branch is a U-Net-style architecture, taking the map and generating a feature of size c for each pixel. The temporal branch consumes the last n seconds of odometry, and via an LSTM outputs a temporal feature also of size c. The LSTM runs once per second. The spatial branch only needs to be run once for each new map, and its output can be stored for further computation. The dot product of the temporal feature and the spatial feature is computed for each pixel, generating location likelihoods for all pixels in the map. We train this network with an MSE loss computed against feasible user locations. Feasible locations are calculated from the last n seconds of ground truth positions, as opposed to the odometry estimates which the network receives. Our work has three experimental goals. First, to quantify how well we reduce inertial odometry drift for pedestrians. We test this with the idle dataset. Second, we want to compare our method to Bluetooth pedestrian localization, which requires instrumenting an environment with Bluetooth beacons. Third, we see if our method can transfer to a different type of odometry, in this case, wheel odometry from a turtle bot. Here we show the results of our method in red against the ground truth in blue. Several other baselines are also shown, including pedestrian dead reckoning, deep inertial odometry, and our same particle filter, but with a heuristic prior drawn from the literature, as opposed to our learned prior. Our method is able to track the ground truth much more accurately throughout the course of this 10-minute trajectory as the user walks around the building. Quantitatively, our method outperforms other methods across all buildings in our test set, consisting of several hours of 10-minute pedestrian trajectories. ATE is the average trajectory error throughout the whole path. EE is the error at the end of the trajectory, indicating how much overall drift has been accumulated or corrected for. Our method outperforms all other methods, with the only exception being an end error for building 3, where our method experiences failures near the end of a few test trajectories, leading to a slightly worse performance than other methods. Otherwise, our method is extremely performant, particularly in building 2, where it outperforms other methods significantly. We now look at our performance relative to a Bluetooth localization system on a smaller data set of trajectories where both IMU and Bluetooth beacon data was collected. These plots show mean localization error on the y-axis of different pedestrian tracking methods in 2 different buildings. As the x-axis increases, Bluetooth-based methods are allowed to utilize more and more beacons for tracking during their processing. Our method in green and the pure inertial odometry baseline in blue do not rely on Bluetooth beacons and are thus independent of the number of beacons available. Variance is shown by the shaded regions. At low beacon counts, our method, green, is able to match performance with Bluetooth methods, orange and red, without the instrumentation of the environment required by Bluetooth methods. Even at high beacon densities, so further towards the right on the x-axis, which become infeasible to physically maintain for larger areas, our method maintains close performance to the Bluetooth methods. Here, we transfer our method to differential wheel odometry instead of pedestrian inertial odometry, without retraining our map prior network. The results show that our method, in red, is able to track the blue ground truth much more successfully than other methods, removing the heading error responsible for much of the odometry error for the robot. Qualitatively, our method achieves the lowest error in both buildings and in both metrics, without requiring any retraining for this new environment. In fact, error levels are approximately halved compared to next best performing methods. In summary, our learned map prior leads to significant improvements in pedestrian inertial localization with no additional sensing. This improves results to the point that we approach the performance level of Bluetooth beacon-based localization. Additionally, we show the ability of our method to generalize to different types of odometry with very few changes. Thanks.